Thank you, Mahmoud, for introducing me. I will try to go quickly because the time is sometimes congested. Today we'll talk about load displacement response of piles under different loading conditions. Our content, we will talk about introduction, small strain and operational soil stiffness, case study, construction of pile in soft soils, database of pile load tests, back analysis of pile load tests using numerical modeling, conclusions. Nowadays, special piles are used in megastructures. The major role of piles to transfer the load from the superstructure to stable subsoil and the displacement against applied load, and the displacement of the structure is within serviceability limits. The displacement is a stringent design criteria in large structures, and the soil stiffness is the key geotechnical parameter for the calculation of the displacement. So, proper understanding of soil stiffness is necessary for suitable estimation of foundation displacement. Actually, the soil stiffness depends on many factors like stress history, soil type, stress level, initial stress state, and also soil stiffness decreases in nonlinear manner with increasing strain level. Subsequently, the soil stiffness should be related to the corresponding strain level when analyzing geotechnical problems. Also, the response of pile under loading condition depends on several factors, including pile geometry, instillation effect, and the nonlinear behavior of soil. So, the back analysis of static pile load tests is a valuable technique to consider all factors influencing the pile response. Consequently, the operational soil stiffness can be back calculated from the load displacement curves. The soil stiffness can be evaluated using undisturbed samples from lab testing or indirectly from empirical correlation using in situ testing or directly from in situ geophysical testing. Soil stiffness can be presented by a number of elastic modulus, Young modulus, shear modulus, constraint modulus, and also every modulus can be expressed and secant, tangent, loading, unloading, and the maximum. In fact, the quality of specimen is very expensive, and the disturbance of sample is unavoidable. The in situ test attempted to obtain the deformation soil modulus in its natural state. However, the assessment of the appropriate modulus value has a major difficulty because there are factors affecting the assessment of soil modulus, like degree of disturbance, degree of drainage, nonlinear stress strain of soil anisotropy, strain rate dependent. So the modulus magnitude is not a unique value. So the full-scale tests are the best way to obtain the soil stiffness. In this figure, Paul Mean at 2001 show the typical stress strain curve and the stiffness of the soil corresponding to each in situ test at different stress strain level. And also the factor of safety associated to each soil modulus from the maximum soil stiffness to the minimum soil stiffness. Most of penetration tests provide the measurement at the maximum strength of the soil at factor 50 equal 1. While pressure meter tests and the dilatometer tests get this measurement earlier on the curve. But comparing to the most of penetration tests like SPT, CPT, which is maybe beyond our geotechnical deformation problem version at factor 50 equal 4. So the small strain stiffness is considered as a reference value for all soil at given confining stress state, void ratio, and the corresponding strain level. Accordingly, other modulus can be compared to small strain shear modulus because it is a fundamental property for all types of soil, and it is the same for static and dynamic loading condition, and it is independent of drainage condition, and it is also insensitive to an over-concentration ratio of both sand and clay. So, Mean at 1995 stated Gmax provides a universal reference of stiffness for deformation problem that can be applied to foundation systems. Koch at 1979 mentioned the behavior of deep foundations in terms of displacement, starting from the initial value of loading till the ultimate pile capacity is influenced by the operative soil shear models. After that, various of researchers over the years from 1986 to 2019 provide techniques to forecast the displacement of foundation using the shear modulus at working stress-strain level through the back analysis of load tests. Here, Pradi and Polvalenta in 2005 proposed a semi-empirical method to forecast the load displacement of axially loaded pile via back analysis of pile load tests using an elastic solution, Randolph and Roth at 1978. Niazi and Domain refined the methodology by integration soil plasticity and adding well-documented data. Our case study is at Prol site. It is located on the Mediterranean Sea in the north coast of Egypt. It is on the western side of Nile Delta, and the eastern side of the Nile Rosita Nile branch. This is site layout. It consists of 4 modules with angular buildings. The side length about 1 kilo and width is about half kilo. We divided the modules to zones A and B and C to reduce the soil variability during the study. Actually, the site has an intensive site investigation survey. We have in-situ testing like SPT, 75 SPT. We have 124 CBTU, and we have also geophysical tests like 12 downhole tests and 8 seismic CBT. Also, we have intensive lab testing, we have index properties, we have odometer tests to get all pre-construction pressure, and we have also unconfined compression test and UU and DCU triaxial tests to get soil shear strength. Here, the representative subsurface ground profile, the upper 14 meters, it consists of very loose to loose sand and very soft to soft clay. While below the 14 meters, we have medium dense sand, followed by dense to very dense sand and very stiff to hard clay. Construction of pile in such soft soil needs precautions. So we had to use a long temporary casing to prevent the collapsibility of soft soil inside the pile construction. Also, we have to monitor the groundwater table and the tidal effect during construction. So because the drilling fluid should be at least 1 meter above the groundwater table, and also the tidal effect due to water flow or water movement inside the soil increase the potential of collapsibility of soft soil inside the pile. And also it is affected on the pile construction sequence. We have to first start with the perimeter piles, then go inside to make like a wall to minimize the water movement effect. Also, we make like trench stability for pile. We had to use apparite to increase the density of the drilling fluid to make more stabilization for the pile during construction. Also, in the non-working compression tests, we use double sleeve. It is a permanent casing. It composed of 2 casing or 2 liner with a gap to prevent the effect of soft soil on the pile response on the under axial compression. And this is the final product after taking all these precautions. Here we have a 17 database of pilot tests. We have 4 non-working compression, we have 5 working compression, we have 2 non-working tension and 2 working tension and 4 non-working lateral. The diameter 0.8 and 1 meters, and the length ranges from 33 to 42 meters. Non-working compression and non-working tension is loaded to 200% of working load, and working tension and working compression loaded to 150% of working load, while the non-working lateral loaded up to 700% of working load. These are figures of site pilot test. This is a compression pilot test, and this is a lateral fixed free lateral test. This is a free pile, and this is the fixed pile. This is a support pile. Make a fixation through this truss to apply to simulate the fixation of pile head. And this is the jack, and this is a beam transfer the load from the jack to free pile head. This is a pile load, a tension pile load test. This is the reinforcement of pile, and this is it's called the feedback bar to transfer the load from the jack to the pile itself. This is our operation. This is our flow chart to get the operational soil stiffness. First, we selected soil parameters. Then we assume reduction factor equal 1 for the first iteration. Then we assign soil parameters in numerical model. Then we get the output load displacement curve and comparing it with the field load displacement curve. If we have a good matching, we already get the operative soil stiffness and the reduction factor. If we don't have matching, we make another iteration to get the good agreement or good matching between field and the output load displacement curve. Here I will present the example for case study in the database. We have a pile compression. It is 1 meter diameter, length is 35, and settlement is head settlement is 51.5 millimeter. This is adjacent pore hole, and this is we use double sleeve in the soft soil to prevent its effect. Here the adjacent soil investigation. We have SPT and the CBTU data and the shear wave velocity. Then we get the soil parameters, CU and the internal friction angle of sand and small and G maximum from shear wave velocity. Then we make a numerical modeling using Praxis 3D. We simulate the pile as a volume pile, and we use interface extension to get a smooth stress escalation at the tip of the pile. Here we show the pile, the meshing of the model. We use medium mesh overall with local refinement around the pile. Here our selected model geometry is not affected as the output of load displacement curve. Here to consider the effect of double sleeve, we show relative shear stresses. There is no shear stresses mobilized in the double sleeve zone, but after in the pile soil zone we get the mobilized shear stresses, and we get a smooth curves, smooth stress oscillation due to extension of interface. This is the output. The red line is the output from the Praxis, and this point is the field data. We have a good matching at reduction factor equal 0.7. Also, this is example for lateral and tension. We have here also a good matching for both. This figure shows the soil modulus estimated through the literature using standard SPT value to get E-trend for cohesionless soil using Kalhawa and Main at 1990 correlations and Ashto 1996. And we used Termat with Vermeer and Verger at 1985 to get undrained soil modulus for cohesive soil based on undrained shear strength and the plasticity index. As we see here, the estimated soil stiffness is underestimated value. Consequently, the expected settlement is overestimated value. And this is matched with what Main it all been published at 2001. Also, we go through the literature. We found backfigured soil stiffness from scale test, load tests. Kashan and Kalhawi at 2001 present a correlation between E undrained over undrained shear strength versus a depth ratio. Depth ratio is a shaft depth of over the pile diameter for uplift for tension and compression tests. Here he put lower and upper limits. The lower limit equal 100, but for upper limit it ranges from 5,000 for low values of D over B and till 1,000 with increasing D over B ratio. We put our data on the same figure, and we observe that the value of E over under shear strength has a wide range for low depth, for low D over B, and increasing was and has a narrow range with increasing D over B, and this is matching with the trend line. This is matching between upper and lower limits proposed by Kashan Kalhawi. Also, again, Kashan Kalhawi at 2002 provided another figure for E trend over unit side resistance versus depth ratio with the same also for uplift and compression, and presented the lower limit and upper limit. Here we get our data on the same figure, but the unit size resistance is classified open the Bezidio strain, which is the pile head settlement over diameter ratio. We take it as ultimate side resistance when the W over D percentage over exceeds 1%, while for W over D less than 1%, we take it as a percentage of it. So we get three figures for non-working compression and working compression and the non-working tension and working tension. The ranges of values for E drained over unit size resistance ranges from 2,000 to 6,000 was average 3,000. But for working compression, it is beyond the upper limit of Kashan and Kalhawi. It is ranges from 5,000 to 15,000 with an average value equal 10,000. And finally, for tension, it is in the range of upper and lower limit, but and it is ranges from about 100 to 6,000 with an average value 3,000. Here we get the reduction factor for G over Gmax versus immobilized load, which is the test load over the ultimate load of pile capacity using analytical approaches. This is mobilized load is reciprocal of factor of safety. So when the factor of safety equal 2, the reduction factor equal 1. This means the actual soil stiffness equals the maximum soil stiffness, while within decreasing the factor of safety till 1, the reduction factor equal from 70 to 80% of the maximum soil stiffness. Also for tension, for non-working tension, we found the reduction factor equal 0.45 and 0.9 versus immobilized load ranges from 0.4 and to 0.5, and when the mobilized load lower than 0.4, the reduction factor equal 1. For lateral tests, we observe that when the Q ultimate equal 0.65, the reduction factor equal 0.5, while when this value under or lower than 0.4, the reduction factor equal 1. So our conclusions: the back-figure soil stiffness is higher than the estimated soil stiffness, and the estimated soil and the estimated soil stiffness is underestimated value. So the estimated soil settlement is overestimated. And the back-figure soil stiffness equals a small strain for tested pile with a higher factor of safety under test load, and the behavior of pile are similar to pile designed as conventional capacity-based approach. On the other hand, the back-figure soil stiffness for tested pile are tested under low factor of safety is a percentage of maximum soil stiffness, and it is revealed the pile considered as settlement reducer. This table summarizes the reduction factor, the reduction soil stiffness factor. Here, the values of E undrained over under shear strength has a wide range for small depth ratio, and range decreases with increasing depth ratio. And furthermore, these values are matching with the trend of upper and lower limits. Finally, the E trend over unit size resistance are matching with the trend, and we have ranges or open the loading type. Thank you. I hope I will not make quickly, but the time is very congested.
Yeah, it's very nice presentation, Ahmed, and very nice results. Yeah.
I hope I do good.
Yeah, you did. Any question about that or anything related with the pile? if you have any question related with piles, with construction, Ahmed have a lot of experience with that. Thank you.
Thank you very much.
Thank you, Ahmed. Thank you all.
You are welcome.
Yeah, this is lead us to the end of the due Ramadan day, and see you tomorrow. Tomorrow will be Ahmed from McGill University, and maybe I will join that instead of today because of Dr. Yasser joining us today. So yeah, have a good time. See you all. Thank you.